In this video, we're going to talk about another carbonyl condensation reaction known as the Claisen condensation, or the Claisen reaction. In this case, we're generating an enolate, which could be of an ester or a ketone or something else. And the electrophile in this case is going to be an ester. Right? So the aldol, we had the electrophile be an aldehyde or sometimes a ketone. In this case, now the electrophile is in fact an ester. And so what that gives us as a product is a beta ketoester. Or in the case of a ketone enolate, it would be a 1,3-diketone. Okay, so how does this work? Well, it's very similar to what we've seen before. So the first thing that you need to have is a carbonyl that is capable of undergoing deprotonation. So in this case, we have methoxide, and as we saw before, that actually needs to match up with the ester groups that you have because you have the ability to do transesterifications. But that's just sort of a detail. In this case, we've got methoxide. We deprotonate to give the ester enolate. Okay. And then we're simply going to let that enolate do a nucleophilic attack onto our other ester component. Okay, so this is going to be now, from the point of view of the electrophile, it's a nucleophilic acyl substitution reaction. Okay, so that addition will happen. Okay, so here's our tetrahedral intermediate. Okay, so this was the enolate that added into this carbonyl here. So here's our tetrahedral intermediate. And then, just like we've seen before, this is then going to collapse down, and we're going to spit off methoxide. Okay, and so then that's going to give us our beta keto ester product. Okay, so we just spit off methoxide. But now it turns out that in the flask, even though this is the product, in the flask things aren't done yet, because what we've just generated is a beta keto ester. So we were first dealing with just normal esters, things with a relatively low acidity, and now we've generated a 1,3-dicarbonyl, which we've talked about is now much more acidic. So what's going to happen here is that this additional proton is going to get deprotonated. Okay, so you're actually going to form the enolate of the beta keto ester in the flask as this reaction is occurring. Okay, so this is how this intermediate is going to sit around. Okay, and then once you work this up with proton, right, at the end of the day, then you can actually get to the to isolate the beta keto ester. So why do I bring this up? Well, it turns out that you actually have to be able to do that deprotonation, because if your beta keto ester can't form the enolate, then this process isn't favorable. It'll actually reverse all the way back. Okay, so all of these are reversible arrows. But under these conditions with sodium methoxide, this is then not reversible. Okay, so it's this enolization that makes the Claisen condensation stick, and then you can work it up to get the product. If you can't do that enolization, then you won't be able to have a Claisen condensation go forward. So let me just quickly show you an example of that. So if I were to take this ester, okay, and I'm just going to do a dimerization, sodium methoxide, right? So I can enolize because there's a alpha proton there, and the Claisen condensation product would look like this. Right, so one equivalent of that ester added into another equivalent there. and we would have spit off ethanol. But in this case, there's no alpha proton, okay? So this isn't going to be a stable compound because ethoxide can add back into that carbonyl and they can split back apart. Okay, it's just the reverse mechanism. But it turns out that the Claisen condensation is not favorable, actually. Okay, so you won't be able to get this reaction to go. This will be no product. And what that means is there will be some of that formed, but the equilibrium is very much to the side of the starting material. Okay, so for a Claisen condensation, you basically can't have two alpha substituents on the enolate component, okay? So let me just show you two reactions that actually can work for the Claisen condensation. So if we just had instead ethyl acetate, right? So here now there's no substituents in that alpha position. If I take ethyl acetate and I treat that with sodium ethoxide, this can absolutely do a Claisen condensation, and I will get to, in fact, ethyl acetoacetate. Okay, so this is a good reaction. That'll go just fine. Another one, if we have just a single alpha substituent, okay, same conditions, sodium ethoxide. This can also proceed. Okay, so we can get to this somewhat more complex Claisen condensation product. But if I were to do one, again, with two alpha substituents, that can't go forward. That's not going to be possible, okay? All right, so again, we're talking about just dimerizing the same ester. What would happen if we wanted two different esters? Okay, we talked about this issue with the aldol reaction, and the same thing goes for the Claisen condensation. Right? What if we want two different partners? Okay, so what are we going to do? So of course this is going to be called a mixed Claisen condensation. And we sort of run into the same issue with the aldol, that if we have two different esters and they both can be enolized, and they, that they both can serve as Claisen partners, you're going to just simply get a mixture. So the way around that is, for example, you could use one component that can't enolize, right? So we could think about using ester like this, ethyl benzoate, okay? And then we could pair that with another ester that can enolize, okay? And so this would give a Claisen condensation product like this. Okay, so this would be fine. The problem, of course, is that this reaction can occur, but also this ethyl acetate could add into itself. So you'd need to use an excess of the electrophilic component if you want to get a good proportion of this product versus the one where you would dimerize that component. On the other hand, you could also use a ketone for this type of process. So if you did, for example, cyclohexanone and ethyl benzoate, right? So now you've got a good situation where this can't enolize, and this can't serve as a Claisen electrophile because it's not an ester. Of course, it could do a self-aldol, so you're going to have to take that into account and probably still use an excess of the ester. But you certainly could think about getting a reasonable selectivity of this type of product here, this 1,3-diketone. But in reality, okay, so in either of these cases, probably the best bet here, if you want to get a mixed Claisen, is to actually deprotonate what is going to be your nucleophile with LDA. Okay, so forget about the sodium methoxide thing, which is only relying on equilibrium. Use LDA and you can decide which one you're going to deprotonate and then throw in your electrophilic ester. And for the most part, that's probably going to give a good product selectivity. Okay, so that's the Claisen condensation, and really the key part here is to understand that you have to be able to deprotonate these intermediates in the flask in order to get it to stick. If they're substituted, if they're disubstituted there, you won't be able to isolate them under those basic conditions because they simply revert back.